Okay, our simple average assumes the same number of each of these things. Okay, so if we took the example we were looking at, whatever it was, Tuesday. Okay, we had our set. We had 1 and we had 2. Okay, our simple average just goes through and says, well, I add up the numbers, whatever's in my set, and I divide by the total numbers in my set, which in this case is 2, and I would end up with the raucously difficult answer of 1.5, okay, or 3 halves, however you want to look at it. Okay. When we have very few numbers in our set, the simple average is relatively straightforward and easy to manipulate, particularly if they're all different. Okay, we'll almost always do a simple average if we have different numbers. But what happens if we expand that set to, say, 4 numbers? Right. 3 1s and a 2. Well, if I go through and do the simple average calculation, I have to go through and say 1 plus 1 plus 1, plus 2. And I need to divide by the now total numbers within my set. How many numbers are there? 4. And then I can punch that in the calculator and get whatever the answer is. Yeah, whatever the answer is. Okay? That answer, should it be closer to 1 or 2? Why closer to 1? There's more 1s in our set. Okay? So that's our simple average. The kind of weighted average wants to take into consideration how many of each of those things are present. Right? And so what we're going to try and do is evaluate how these things are different and how they're the same. So our weighted average, okay, I want to take the amount of each of the integers, or each time they showed up, and kind of factor that in independent. Okay, so I have 2 values in my set. I have 1 and I have 2. Okay. How many times did my 1 show up? Okay, it showed up 3 times, so I'll multiply 3 times my value of 1, but it showed 3 times out of how many? 4 possible options. So far, so good?
Why did you do that?
Okay. That's just what we're trying to do, is figure out how many times it showed up. So it's the value, how many times did it show up, how many times could it possibly have shown up. Okay. So if all of them were 1s, what would I be multiplying that 1 by? 4 divided by 4. 100% of the time, it was 1. Since it has a 2, something else varies in it. There's only 3 1s, so I've got 3 1s out of a possible 4. Okay. What about the 2? How many times did 2 show up? Once out of a possible 4 times. Okay. I can then add those values up, or do the calculations, add them up, and that will get what answer? The weighted average, which will be exactly the same thing as if we did the simple average. No difference. Okay. You might say, well, the simple average just had a bunch of addition. The weighted average has a bunch of multiplication. Multiplication is more confusing than addition. Let's just do the addition. Right? Everybody, like, that's fair? Okay. So let's do this now. Okay. What was that? And it's too hard to draw. Okay. A lot more 1s. Okay. We'd still have to go through this counting process. But this is where I can add another layer of information to this. Instead of looking at each of the numbers within the set, I could also tell you that 90% of the values in there are 1, 10% of them are 2. Okay? So we could go through and determine those percentages by counting everything out. Somebody's already gone through and done that and told you that 90% are 1, 10% are 2. If we do the simple average, we have to add every single one of those 1s up, every single one of those 2s, and then make sure we counted all of them so that we can then divide by the appropriate amount. Okay. Does our weighted average give us kind of a cheat if we're given these percentages? Okay. Well, does our weighted average have a percentage in it? Actually, it does.
Oh, it does. Yeah.
3/4 and 1/4. 3/4 is really 0.75 times 1 plus 1/4, 0.25 times 2. What is 0.75 plus 0.25? 1, representing 100%. Percent. Okay, I still don't see percent in there. If we look at the 90, how do we know that 90 is a percent? It shows a percent sign. That's how I know it's a percent. Okay. Do I see a percent sign anywhere else up here? No. Okay, so let's evaluate what that percent means. Percent. What does per mean? Division. What is cent? 100. So what is 90% really saying? 90 parts in 100. What is 0.75 converted to a percent? 75 parts per 100. Whoa. The percents get factored into our weighted average. Mathematically, it's all there. It's just a question of now plugging and chugging. Okay, so for those of you going, wow, that was a lot of addition, all that fun stuff, let's just clear that all away and simplify this. Okay, our percent of A times our value of A plus the percent of B times our value of B, okay, plus our percent, technically, of C. Wah, too many parentheses. Let's do D, because C is too confusing. Percent of D times the value of D. I can continue to add for however many times it shows up. This then equals what? The percents summed would equal 100, but it's not the percents. I'm multiplying by the values. What do I get? I get the average. Okay. It's known as the weighted average because I calculated it using the percent values. That's it. So now it's just a question of plugging and chugging. It's doing the exact same thing we did with the simple average and then breaking it down and looking at how we could manipulate our simple average to get to that. But that's it. Okay. Why was this important? Important? Why was this important? Okay. Where did we see a weighted average show up on Tuesday? It's the atomic mass on the periodic table. Not the mass number. I don't want to open that can again. Okay. Not the mass number, but the atomic mass. Our periodic table gives us the weighted average. Was it a hand, or were you answering? Okay, just going to make sure. Okay. So now that we've got a general idea on where this is coming from, let's attempt to use it. Let's see, do I have two questions here? Nope, I only have one. Whoops, you didn't see that. Okay. Gallium has two isotopes. Okay. And this will become confusing if it wasn't confusing already. We have gallium-69. Okay. That symbol, 69, was our mass number, then the GA for gallium, okay, said gallium-69, okay, with a mass of 68.926 AMU. What is AMU? Who cares? Really irrelevant to what we're trying to do here. Okay? For those of you that did shout out the answer, you were correct. It's the atomic mass unit. So we're looking at a mass. The mass for gallium-69 is 68.926 atomic mass units. Okay? So some kind of mass measurement. Right? And it has a 60.11% abundance. Gallium-71 and gallium-71. Oh, that's the second isotope. English, right? Okay, there's two isotopes, gallium-69 and gallium-71. Okay. What is the mass of gallium-71 in AMUs, so we're keeping the same units, to 4 significant digits? Okay. So significant digits is a little bit challenging. I just want 4 numbers, okay, for the mass of gallium-71. Okay. This is on the weighted averages slide, so maybe using the formula we just looked at might be helpful. So let's rewrite that. Percent of A times A plus percent of B times B. Do I want to do another plus? There's only 2 isotopes, which means there's only 2 things I have to add with each other. I don't know why I put that other parentheses in there, so let's fix that. What must this equal?
100.
Keep going to the 100. Careful.
169.
The average. Okay. Okay, that's our formula. Let's take the information from the question and start to slide that into this to match this up. What is A? It's, I won't quite accept one part of the formula. Aspen, I think you were going for something. What is A? I don't accept the AMU either. It's not the percentage either. It's on the mass. It's the gallium. A is our species.
Oh, so 69.
So which species is A? Does it matter? No. Pick it and be consistent. Okay. So gallium-69 is A. Okay. What is the percent of gallium-69? What is the A value? Okay. What are we taking the average of in this case? It's the unit, our mass. What was the mass for A? Right? I do that one? Yeah. Plus what? What is B? B is our gallium-71. It's the other species. What is the percent of B? So I'm a little puzzled. 39. I don't see 39 up there. Where are you getting that number from?
Because 100% minus 60.11.
Why are you doing that?
Because the gallium-69 is 60% of all gallium, and there's only 2 isotopes, so it's mass.
So if all of our gallium is down to 2 things, and I know one of them is 60%, what does the other one have to be? The remaining. What is my total percentage? Percent? 100. Okay. So I can take 100 minus the 60.11, and I would get the percent of B. Said 39 point what? 89. Okay, so cool. I could now put that value in here. What is our value for B? And it is really hot in here. It's what we're solving for. So, X. You don't like X? Pick Y. You don't like Y? Pick Z. Okay. You could leave it as B. You could draw it as a little heart. Doesn't matter. That's what you're solving for. What does this need to equal? The average. Okay, so the average is given up there. Remember, your average atomic mass is provided where? On the periodic table, which is always given to you. The periodic table is a very useful tool. You are assumed to be able to find information on it. Okay? So in this case, we would then need to look up gallium on the periodic table, which is element 31, and it has a mass of 69.72.
Why is you have gallium 69, gallium 71?
What are gallium 69 and gallium 71? Isotopes. Continue. Okay. The periodic table is the element, so it's the combination of all of our isotopes. Okay, so now what do we do? Solve. And we end up coming up with the wrong answer. Okay, if we enter it exactly as is. Some of you may have already fixed the issue. Where's the percent button on your calculator?
Well, you just,
There isn't one, so we have to mathematically convert it. What did percent mean?
you just move the decimal place.
Per 100.
So is that 68.926 also a percentage?
Do you have to divide by 100 or can you move the decimal?
Well, multiple questions. 68.926, is that a percent? Do we see the percent written next to it? No. So is it a percent? No. What is it? It's our AMU. What did we say AMU was? A mass. Okay? And we really don't care. It's something that we're taking the average of. Okay? So we can then set it up. This will now work. So a couple questions popped up. Do we have to divide by 100? Well, what do you mean by have to? If I go back to the percent and just say 60.11, no, you have to divide by 100. Okay? You have to in that case. If, however, by saying, do I have to divide by 100 if I shift the decimal 2 places?
No.
You already divided by 100. That's why you shifted the decimal 2 places. Some of you are able to do the division by 100 in your head. That's fine. Go ahead and do that. The reason why I tell you to not do that is during an exam, how many of you are just cool as a cucumber, totally excited, yep, exam, I love this. This is easy. Anybody? No. So your brain has gone to complete futz during an exam. Futz is a word, presumably. Okay. If you don't show that divide by 100, maybe you shifted the decimal 2 other places. Guess what kind of a jerk will have also put that as a multiple choice answer? Okay? You need to know what you're doing and not just randomly punch stuff into the calculator. Write down your work. You can track your work. You don't have to worry about, oh, I shifted the decimal the wrong way, because you can see your work come out for you. Okay? The answer that comes out of this, what did we get for x? I think 70.9165. Okay. We said 4 significant figures, which you will talk about in the lab video, which in theory you're watching before lab next week. We will also talk about it when we get to it, really importantly, in lecture in a couple units. 4 significant figures means 1, 2, 3, 4. My answer can only get reported to that last place, so this 6 and the 5 get crossed off, but because the 6 is big, I round up, and this becomes 2. There's my answer officially with AMUs, which I won't yell at you yet for leaving off.
Significant figures always go from left to right.
Significant figures always go left to right, yes. Okay. Why would they always go left to right? Read the first line for me, please.
Simple average.
Wait. Where did you start? Just where did you start?
A.
Which was where?
Left to right.
Left to right. Why do we read left to right? Because that's how we read. That's our default. So when we look at our numbers, we'll read them left to right. Okay? Questions about that? Yes, then yes.
So you divide by 100, you added, you multiplied those, you added 3 there, and you add to it, and you divided by 0.72 there, right?
think you're asking about the actual algebra steps. I don't have enough space to write that all in there.
Yeah, well, I mean, I was just wondering, like, how'd you get 17?
Okay, a request has been made for the algebra. I will go through and work that out because we do have varying limits on what our math backgrounds are, so let's go ahead and take a look at that. How would I go through and do this? I don't like calculators, so what I would try and do is simplify things as quickly as possible. Okay. My first step, interestingly enough, would be to actually multiply both sides by 100. Because when I multiply the left side by 100, that 100 has to multiply through, cancels, and cancels. So the left side, no hundreds, and the right side gets multiplied by 100. So the answer I would end up with would be, now I actually got to look, 60.11 times, come on. My pen's having a fun day today. Where'd it go? 68.926 plus 39.89 times x equals, and I'm going to do the thing that I told you not to do. I'm just going to shift that decimal. Okay, multiplying that by 100. Yeah? Algebra step number 1. That's my step.
So are you multiplying this entire thing on the left side of the...
Left side and right side.
Okay, so the left side gets multiplied by 100, and then just the 69.72 gets...
Because that's the only thing on the right-hand
Okay.
side. At this point, I want to isolate terms. X, I want to get all by itself. So the first thing I will do is then subtract by that horrendous number. And since I didn't actually write it down, I'll have to do all this stupid stuff. 8.26. Then means I subtract it from over here, 60.11 times. Anybody that actually did that math would be much appreciated. 926. I would have 39.89 times x equals, it's friggin' 69.72 minus quantity 60.11 times 68.926. Divide both sides by 39.89. There's my algebra. Probably would have shortened some of that with the calculator.
I mean, that's what
But
I figured.
that's how I would do
Just
it.
making sure.
Yep. Okay. Everybody good?
You came up with 70.92.
70.92, yeah. I think the calculator spit out, according to the general populace, was 70.9165. Okay.
So you let us use our calculators on like tests and stuff, right?
Only if you stand while using them. No, yeah, you can absolutely use your calculator on an exam. It would be kind of entertaining to watch you stand. No, I wouldn't make you do that. Yeah, you can use your calculator. Okay. Other questions on that?
You always round the last,
The rounding I'm going to hold off on. We'll address that later when we actually really start bringing numbers in. We don't get a lot of calculations showing up in the first section. It pops up in a few places. I won't be throwing curveballs at you with rounding issues to worry about. Okay.
So when you do get the calculations and stuff in chemistry, is it mostly something like that?
When we do get to calculations in chemistry, there are rules for how you do those calculations. If you would like a jump start on that, that's the play pause it video for the lab you're doing next week. Lab next week, we'll actually talk about it. Oh, and I forgot to check this. So when it comes to quizzes, you all are slobs. Just kind of put it out there. And I don't want to deal with all your random loose leaf pieces of paper, because some people have the spiral notebook, they rip it out, you got the spiral things all over the place, makes a big mess. So if we do a quiz in class, which we will do, I just happen to not prepare that appropriately, I cut a little quarter sheet of paper and I pass that out. Okay? So instead of this actually being on the record as a quiz, we'll just make it off the record, take a swing at it. See what you can come up with. I've told you to start working on naming elements. This gets you a little bit of review. Let's see what we can come up with. What do you think? Provide the elemental name for the following symbols. N. Well, that's nice. It comes right off of the N. That's cool. The name for the elemental symbol of Na. Natrium. Oh, wait, that's in Russian. Sodium. Yeah, if you're wondering where the Na came from, it's because it is known as natrium in other languages. So sodium, Br, bromine. Yeah, just make it up. Say it with confidence, no one will know. Nickel, silver, potassium. Okay. Any ideas why I would potentially ask those three? They all begin with N, and everybody tends to get them confused. Okay? Which means they also have a very high frequency of showing up on exams. Okay? So any element that either has similar symbols to other elements, those tend to be red flags for going on to exams. The other one are ones where things don't match up, like Na and sodium, okay? Where we don't get a direct connect across. Kind of make sense? Yes? You do not need to memorize the number, because the number will be on your periodic table.
We just need to memorize the element and the symbol.
Name and symbol. That's what you need at this point. We will keep layering stuff on, so don't get too excited about
Up
that.
to where?
It's not an up to. There's a list on Canvas that says which elements. It's the list, I think, is 50 or 60 of them that the department decided was useful to memorize. Because I'm already making enemies. A safe question?
Yeah.
Okay.
On tests, are we allowed to use our own periodic table?
No, you will have a periodic table provided for you. Yeah. It is very similar to this. The only thing it doesn't have is the color coding. So instead I put in symbols. If you take a look at exam 1, the one that's posted on Canvas, you can see the periodic table that you'll be given. Okay. That said, if you want to add information to that periodic table before you start the test, okay, and by before, I mean before you actually start reading the rest of the test. You still got to write your name on it. It's not like, hey, can I get the test so I can write some stuff down? It's not that. Okay. Test passed out, you get your names on it, and then you can write whatever you want, okay, which I highly encourage and recommend. Okay. Brain purge. What is the most important step of the scientific method? All together, all at the same time, with one answer? Failure. Come on. We just talked about failure a whole bunch. It's all about failure. Right. Failure is the part that we have to deal with the most. That's the one that we need to work with. Okay? Yes, the other parts are important. And yes, this is an opinion. Okay, so you're not wrong if you said something other than failure. I think you're wrong. Okay. But my opinion, thankfully, doesn't matter. Okay? Questions about that? Okay. So, what we'll now transition into, because we've really covered only the first half of Chapter 4, we'll transition into Chapter 5, which starts to look a little bit more in detail at the periodic table itself and looking at trends and patterns and stuff like that. Okay? So number one, what do we have up here? What do those look like? Giant freaking mess, but there's some letters in there that look familiar. Those are periodic tables. Okay? Why did we not use those periodic tables? You find them confusing, but the only reason you find them confusing is because you kind of have gotten used to the nice square, easy format. Okay? Each of those periodic tables accents a different piece of information and tries to highlight it and bring it to the forefront. Our standard format does get us a lot of that information. It just tries to keep it cleaner and neater, theoretically, depending on your opinion. Okay? So we have multiple ways to collect the elements and organize them. We just happen to accept the periodic table that's on our roll. Okay? So, how do we come up with these classifications? So we get a bunch of scientists. Don't worry about knowing the names on this one, because I don't think I remember them. Though Dob Reiner sounds kind of cool, so that could be a fun one. he originally discovered that there were groups of elements that reacted very, very similarly. And he noticed that those groups happened in triads. So there'd be 3 to a group, and those 3 would all react along the same kind of vein. They'd all react the same with oxygen or the same with water. And so he started to classify the periodic table according to triads. Well, if we look at the periodic table, does anybody see where you can get just a triad? So a triad being 3 things. And now, there's not 3 rows, there's not 3 columns. I mean, there's not even 3 on the diagonal. Okay? So why did he get 3 and we don't even have a remote understanding of 3?
3 different types of elements.
Yeah, I guess there's 3 different groups, but
No, there's not 3 different groups either. 1, 2, 3, 4.
there weren't as many elements back then.
Came down to the amount of elements. Okay? Since 1829, we've created more elements. That's true, but that's not actually the issue. We actually found ways to purify and identify distinct elements. Okay? 1829 was relatively early in kind of the history of determining the different elements, and so they just didn't have a whole lot. Remember, Dalton had something like 30? Okay? If you only got 30 elements, yeah, triads start to jump out at you. Okay? What is that, 30 years later? I see that name and immediately start thinking Star Wars, unfortunately. Suggested that the 62 elements they had access to should be arranged according to sets of 7, okay, and arranged according to atomic mass. Okay. The sets of 7 was referred to as the law of octaves, and I'm not a musician, but somebody that was a musician tried to correct me, and it still didn't make sense to me. I still don't understand how 7 equals oct, because
I know, it's
oct
8.
is 8. But it's something in music that is correct. I just don't know it. Interesting feature, by that time frame, we were actually missing a column. The last column was missing. Take a look at the second row. If you get rid of that last column, how many are there? Columns? 7. There's our group 7. Starting to notice that if you sectioned it out, that we had 7 distinct kind of categories of reactivities. Okay? And so we started to organize it, and he organized it according to atomic mass. And if we look at our current periodic table, okay, where was the atomic mass found? The bottom of our symbol. So let's take a look at the atomic mass. What happens to the atomic mass as we move through our periodic table? It increases, just like the atomic number. So which one is our periodic table organized after? I always have a hard time finding it. Feel free to jump in and help out at any point. Thank you. Yes. Tellurium and iodine. I always think it's there and then I lose it. 52 to 53, what happened to the mass? Wait, it went down. What was the trend? It's supposed to increase. Is organizing the periodic table according to atomic mass correct? No. Okay. Darn close. There's very few exceptions to it. Okay. Because their chemistry matches the column that they're located in. Okay. That's why they're not switched. Okay. So the atomic mass did not dictate the proper patterns. The atomic number dictated the proper patterns. Okay? How do we end up discovering and finding that? That takes a lot of history and playing around with the individual chemicals to learn something about them. This really comes down to Mendeleev. He is now the father of the periodic table. This name you kind of do need to know. And he proposed that we go according to increasing atomic mass. Okay? Other people had been discussing this, so why does Mendeleev really get the credit for it? Okay? It's not coming down to just, well, I guessed it was this, and so now I'm cool, okay? And everybody else guessed wrong. Okay? The real power behind his guess, which could very well have been just random luck, okay, is that if we look at his organization, we'll notice that we see an element that keeps showing up, this eka. Another eka and another eka. What is that? I believe it's Russian again, because I think it was Russian, and I could be wrong. Anybody speak Russian? Cool. Eka means like. Don't quote me on that. Okay. What do we mean? That symbol is like the element above it. So it is Eka titanium. Okay. This one is Eka aluminum. What does that mean? That means no element had been discovered yet. But in his organization, he said, there's a hole here that something belongs. You other scientists, find it. Okay. And they did. That's one of the reasons why Mendeleev is now kind of all-powerful behind the periodic table. Because it's not that he just said, this is how we're going to organize it, and that's the end of it. Okay? He said, this is how we're going to organize it, and it's so well organized that I can tell you that you haven't discovered all the elements. That's pretty amazing. Okay? That's why we recognize it. Okay? So in our prediction of new elements, Eka silicon was predicted in 1869. Eka silicon is right underneath silicon, also known as element germanium. So if we take a look at our predictions, 1869, germanium was discovered in 1886. Significant time period away to say that Mendeleev probably hadn't discovered it, looked it all up, and then just said oh, I have no idea, that's just me guessing. Okay? So someone had to go through and find it 15 years later. He predicted it to be gray. Oh, that's useful, dude. Okay? I could predict 3/4 of the periodic table is gray. Okay? Atomic mass, 72, 72.6. That's kind of bringing in some numbers. That's pretty cool. Okay? Density, 55, that's 5.32. Okay? This isn't like our AMUs are how heavy these things are. Okay? So that's one thing. Fine, you get how heavy, but what's density? Density is the relationship between how heavy and how large. No idea what the element is, never seen it. Says this is the mass, this is the volume. You put them together, you get this density. And he's right. That's kind of cool. Okay? Melting point, very high. I could probably guess like that too, but okay, 937 degrees Celsius, that's probably very high. I think we can give him that. Formula of the oxide. When we react this compound with oxygen, he predicted it to form in the ratio of 1 of the element to 2 oxygens. Ding, perfect, spot on. Okay? Density of the oxide. I think this is even more mind-blowing. You don't have the element, you don't know its mass, you're guessing the mass. You don't have the elements, you don't have the volume, so you're guessing at the volume. You're then taking this element that you don't know the mass of the volume of, you're reacting it with something else, turns it into a new compound, that you also don't have the mass and volume for, and you predict its density. Like, really? That's pretty insanely cool. That's the power of the periodic table. When we look at elements within a column, they have some very significant hard trends behind them that allow us to predict something about their chemical nature. Fascinating. Okay? That's one of the reasons why we picked the periodic table in its organization today. Okay? Because we have that predictive power. Okay? Noble gases were discovered at a later date. Any idea why it would take so long to discover the gases, the noble gases? Gases makes it more difficult, but oxygen, you get oxygen pretty early on. You get hydrogen pretty early on. How many of you know anybody in the nobility? Wait, what? None of you know anybody in the nobility. Why is that? They're stuck-up jerks and don't want to talk with us. Okay? Common folks, guess what noble gases are? Stuck-up jerks that don't want to talk with anybody. Okay? So they're hidden off in the atmosphere where they're very difficult to get a hold of because they don't react with anything. If they don't react, how do you know you found it? Okay? You're observing the lack of a reaction. That's kind of a challenging thing to nail down. Okay, so it took a little bit of history or a little bit of time to figure that out. Okay, so we got the rest of them in the next 5 years. Okay, then Moseley comes along, discovers nuclear charge. Nuclear charge is what? So another way, what dictates the nuclear charge? The number of protons, which is also known as the atomic number. That's how we've organized our periodic table. okay, is based off of the atomic number. Okay? So the nuclear charge was a more important organization than the atomic mass. That fixed some weird oddities. Okay? Jerry, you said, why weren't iodine and tellurium switched? Okay, well, when we went based off of mass, they probably were switched. And then someone went through and reacted them with oxygen and went, that's not reacting the way it's supposed to. Okay? That's where Moseley goes and says, actually, maybe if you don't do it by mass but nuclear charge, oh, look at that, it fits. Okay? So it's a question of putting all these little puzzle pieces together and organizing them into what we have now. Cool stuff. Okay? Periodic law concept. The properties of an element recur in a repeating pattern when arranged according to increasing atomic number, which is a fancy way of saying if we have the periodic table as it is currently organized, within the column, they all react the same. That's about it. Okay? The next kind of concept that comes out of this that becomes relevant with our periodic table comes down to our electron energy levels. Okay, where did the proton exist? In the nucleus. Where does the electron exist? Outside the nucleus. Where outside the nucleus? Somewhere. Somewhere outside it. Have we defined that yet? No. Why not? Because I think it's confusing, and I want to first understand the periodic table first. We'll come back to it. Okay? Because the periodic table also buries some information about where our electrons exist. Okay? The groups and periods in our elements. A vertical column is referred to as a group or family. Right? That's where our chemistry is the same. The horizontal row is known as the period or the series. It's just a definition that you kind of need to know. Okay? A bit silly, but it is what it is. Okay? So vertical, up, down. Horizontal, left, right. Okay? I'm glad no one laughed at that because that is a concept that is easily confused. Okay? So make sure you get those nailed down correctly. If we also look at that periodic table, you'll notice there's some names popping up along the top. Alkali metals, alkaline earth, noble gases, halogens, transition elements, all the fun stuff. Okay? Because within a column they all react similarly, we can refer to them as a group, okay, or a clan. Okay? You might interact with, say, my family and say we all interact the same. So they're all the McFavelins. There it is. We're doing the same thing with the periodic table. Okay? Those common names that pop up, okay, alkali metals is group 1, or also column 1, starting with lithium. Okay? Hydrogen's a bit weird, so just kind of ignore it. Group 2 are the alkaline earth metals. Okay? Anybody had previous chemistry class? Did you get those two confused? Okay, good. Thank you, because I always get them confused. So this is how I decided to remember. Alkali metals and alkaline earth metals. So metals is the same in both, so I'm going to ignore that. How many words in alkali? 1. Guess what column it's in? 1. Alkaline earth has how many words? 2. Guess what column it's in? 2. Is that incredibly stupid? Yes. But now I remember. Right? How many words in alkali metals? Ignoring the metals. 1, alkali. So column 1. Alkaline earth, 2 words. So column 2. Group 15 and 16 you aren't required to know the name of. I just think they're fun to say, so I like to include them. The elements under nitrogen are known as the... Hey, good. Isn't it kind of fun to say? Pnictogens. The elements under oxygen are known as the chalcogens. Or chalcogens, I don't know. But they're fun to say anyway, so that's why I've got them memorized. You do not need to memorize them. They're just there for fun, because I like to say things weird. What's that? 15 and 16 you do not need to have memorized.
How do you say those again?
Pnictogens and chalcogens. It's kind of fun. I like the pnictogen one too, personally. Pnictogen. It's like I'm casting a spell or something. Group 17. Known as the halogens, yes, you need to know that one. That gets mentioned a lot. Okay. Second to last column, I'll address that in a second. Group 18, the noble gases, starting with helium. Notice we dropped in all those numbers. Those numbers happen to correspond to the column that they're located in. Our periodic table goes from 1 to 18. Okay? Or at least the main group periodic table goes from 1 to 18. So let's get back to Mendeleev because this is also fun. When are we done? 15? 30? 2:15. Okay, cool. Periodic trends, physical properties. Okay, we've got a bunch of information here about lithium, sodium, rubidium, and cesium, which all happen to be group 1, also known as the alkali metals. Cool. What can we predict about francium? So let's put on our little Mendeleev caps, because I envision him wearing a cap. He's also got a big old beard. We can put on our Mendeleev beards. What can we predict about the element francium? Not francium. Why did I say francium? Ignore francium. Potassium. I don't know why there's 2 questions up there. That's ignore the top.
Yeah, you just do like one element minus another element squared because these are different.
Okay. Where's potassium in that list? It's in that giant gray bar. Okay. It is between sodium and rubidium on our periodic table. Okay. So I want to pull a little Mendeleev beard out here, and I want to come up with a reasonable density for potassium. So what do I need to do?
Just find the
Averages, I take the averages of the 2 elements it's in between.
Let's find the density here. Okay, reasonable guess, we could take the average. The average of those 2 should take us out to roughly, what, 1.25? Okay. Is that a reasonable guess? Yeah, somewhere in between those. Okay. If we look at the general trend, as we go from lithium to sodium, what happens to the density? Goes up. Rubidium to cesium? Goes up. Sodium to rubidium? Goes up. So that might make sense for it to go up to 1.25. That is a reasonable guess, okay, based on the information we have at hand. So let's turn it into a multiple choice question.
So
B.
Okay, B. That's pretty darn close to the 1.25 guess. We would guess that. And would we be correct on the test? Yes, you are correct on the test. Okay? Because this is a reasonable guess from the data given. Science is about looking at the data you have, analyzing it, interpreting it, coming up with your hypothesis. That works. Nothing about what we just did was a flawed argument. Okay? Which is what usually causes people to freak out when we remove the gray bar. The actual density for potassium is 0.86. What does that mean about our reasonable guess? It's wrong. So what do we have to do? We have to reevaluate and come up with a new theory to try and explain why potassium has such a lower density. Okay? And yes, we could go through and do that, but that is above the level of the course and not necessary for what we're trying to do here. Use the information at hand, draw the conclusions that you can, and generate a defensible argument. Okay? It's not about being right, it's about being able to explain why you think you're right. If there is a flaw in your argument, that becomes a problem. Okay? If there's no flaw, you win. Kind of make sense? Okay. Chemical properties. Members of a family also have similar chemical properties, which we also kind of addressed. Okay, so if we look at the alkali metals, they all generate the same type of oxide. Okay? We have 2 metals, which I'm abbreviating as M because metal begins with M. It must be too hot in here. Okay. 2 metals for 1 oxygen, and I have a metal oxide, or I'm just not funny. My wife's been saying that too. So if we take a look at all of the alkali metals, lithium oxide, 2 lithiums, 1 oxygen. Sodium oxide, 2 sodiums, 1 oxygen. They all change or hold the same possible formula. Okay? So here's an interesting question then. Write a possible exam question about predicting chemical properties. Okay? So I want an exam question. Remember, most of your exam is multiple choice, so don't give me some short answer nonsense. Okay? Spend till 2 coming up with a possible exam question regarding chemical properties. Inherently obvious with an answer. Like I could go through and say, given the oxide for lithium, potassium, rubidium, cesium, and francium are the oxides shown, what is a possible formula for sodium oxide? I could say, well, NaO, Na2O, NaO2, Na2O2, Na2O3. So let's repeat the question. I didn't even write the question. So the question is, what is formula? It's not going to be perfect English. Formula for, so I can't actually write the formula. That would kind of defeat it. For sodium oxide given this information.
The last one.
And then we have A, B, C, D, E. Everybody guesses B. If everybody guesses the exact same answer, that was a stupid question. Okay.
That was a perfect question.
There's no testing on that. You don't have to understand anything about chemistry, and you would probably guess, well, they're all the same. I'm just going to say it's that one. Okay? That's not a useful test question. Okay? So how could I switch this? Okay? What is the formula for sodium oxide given, let's try this. Sodium, MgO. I don't really know that one, so let's just erase that one. CO2. And for lack of creativity, CO. Is this now a significantly harder question? Yeah. Now, what's the extra piece of information I have to know? I now need to know something about interpreting the periodic table and looking at the column. Okay. Do I have answers? Let's say you get this and you're like, oh crap, I remember Mike talked about it, now I don't remember anything to do. Okay. What could we do right away? I don't even know what a family is, what a periodic table is.
You could eliminate E
Why get rid of E?
because it has nothing up there.
Doesn't match any of the patterns.
Same with D.
Can we get C? Can't really get C, CO2.
We can get rid of A. Well, no.
CO.
Yeah. The C.
So we went from 5 answer choices, 20% chance of getting it right, to now a 33% chance of getting it right. Okay, that's a significant improvement. Okay. Remember how we talked about failure is actually a good thing? The test writer failed to provide decent answers. Take advantage of that failure, get rid of those wrong answers. Okay. Failure is a good thing. We just have to realize it's failure. Okay? So take advantage of that information. Does that make sense? Okay. For those of you curious about tests and what kind of questions could get written, that's what the practice exams are for. Okay? You won't get the exact same question, but what you will get is some permutation thereof. Okay? So instead of just going through and taking the practice exam and saying, well, the answer is this, and then you take it again, well, the answer is this, and you take it again, oh, the answer is this. You've proven that you can now memorize the answer to that question. Okay? You're not going to see the same question. So instead of doing that twice, maybe the third time, instead of taking it again, look at it and be like, how do I change the question so one of those other answers is right? Because if we think about writing new questions, that's a difficult process. So if we already have a question that works, maybe I just tweak the question to make one of the answers valid, and then I've deleted 2 words. That's pretty easy. Right? That's what test writers are doing. Right? We have a question, how do I tweak it? If you're thinking like a test writer, you will have thought of all the permutations that I can do, the test becomes cake. Neat. Make sense? Okay.
So, going back to that.
Yeah.
You'd have to know something about the families to make sure you have it.
So when we ask questions on the test, it's not just well, I'm just going to match whatever random letters show up. There will be some textual information that you should have to have interpreted. Otherwise, it's blind guessing. Yep. So I will always be asking something about chemistry. Should always be asking something about chemistry. Okay. Which takes us now to periodic trends. Okay, the arrangement of the periodic table means that we have physical properties, okay, chemical properties following in regular patterns. Okay, so we can start to draw some knowledge about that organization and come up with some pattern usage. Okay, so let's take a look at the size of an atom. Okay, and I think I briefly mentioned this before. When we talk about the size, what are we measuring? What are we looking at when we think about size and atomic radius? The electrons. Okay, I heard the electrons and I heard the nucleus. Ooh. Do those mean the same thing? No. When you say the electrons, why are you saying that contributes to size?
Their energy and they're all lower, and then so it makes like they're too small.
Okay. Let's go back to the nucleus. Why do you say nucleus? Someone said it over here.
Well, because the periodic table is based off the protons, which are in the nucleus. So I just feel like if you're increasing on one end, if your protons are increasing, well, you're getting more protons, you need more space to put them in. So I just feel like you're based off that.
Okay, so let's pick 1 proton, 1 electron. Okay, opposite charges, right? So like magnets, they would attract. Okay. What happens if I add another proton? What happens to that electron? It gets closer. There's more positive charge, so more positive charge, that's going to suck the electron tighter. So you had an interesting idea as we add more protons, okay, maybe it gets bigger. So we add more protons, if we hold the electrons constant, which is a big challenge, the electrons will actually get drawn closer. Okay. So just adding protons doesn't necessarily contribute to size, okay, which brings in kind of the next part of this. When we're talking about size, we're talking about the volume, the space that it occupies. How big's the nucleus? It is tiny. Remember, if we look at an atom as the superdome, the nucleus is a marble inside it. The marble does contribute all the mass. It's not contributing the size. The size is due to the electrons on the outside. So size is referencing volume, not mass. So we're looking at our electrons. That's our subatomic particle. Okay? So we get 2 trends for our atomic radii when it comes to size. So let's look down a column, okay, or group. Yeah. We go from hydrogen to lithium. What happens to the amount of electrons? And let's assume neutral structures.
The electrons increase.
The electrons go up. We go from 1 electron with hydrogen, neutral, to lithium with 3 hydrogens. The 6 is its mass, protons and neutrons, not electrons. Okay. Potassium would have 19 electrons. So as we go down the column, what happens to the amount of electrons? It increases. So what would we expect to happen to size? It increases. Guess what happens for our trend as we move down a column? It gets bigger. It increases. Awesome. Sweet. Don't we love it? We took a guess. Worked. More electrons. It gets bigger. Sweet. What happens when we move left to right? So we go from lithium to beryllium. What happened to the amount of electrons? It increased. So what would we predict to happen to the size? It should increase. What happens to the size? It decreases. Wait, what? Okay. There's an interesting theory. Let's run with that. You're saying, so now let's write this down, because here's where we started. Down a column, so down C, bigger radius, okay? More electrons, right? Roughly get that notation? Okay. Across row, we got smaller, yeah, R was a bad idea, radius. Okay. Well, left to right is more electrons, so that doesn't work. We can't use the same thing. So you're going to say what? More protons. Okay. If this theory is valid, this also needs to be able to explain going down a column. So let's go back to the column. When I go down a column, my radius increases because I have more protons.
No.
You said electrons.
The electrons do it.
Wait, those are counter. Yeah, something's not adding up. If we use electrons to count, one direction makes sense, the other one does not. If we use nuclear charge, the amount of protons, one direction makes sense and the other does not. So how do we do it? What does that mean is inherently problematic? We are missing some bit of useful information that we have yet to discuss. What comes down to size? Where the electrons are located. Have we discussed where electrons are located? Not yet. So until we understand where electrons are located, can we make sense of the actual trends for size? No. Okay? So our trends, and these are true, your atomic radius increases as you go down a group. Okay? Atomic radius decreases as you go left to right across a period.
What is the radius?
Okay? The radius, what made up the radius? The electrons. The more electrons you have, the bigger you get. Okay? Why would you get bigger with more electrons?
There's less.
Why do you need more space? There's someone said it over here. More negative charge. And what does the negative charge do when it gets near another negative charge? It repels away. So the more negative you put in, the more space it has to occupy because they have to get further away from each other.
So the electrons are counted by the atomic number?
The electrons in a neutral molecule are counted by the atomic number. So we have to specify very specifically that we have no charge on that molecule. Okay. So we've got our general trends. Okay, we can see pictures of this to verify it. Okay, but we don't have an explanation yet. Okay. The next thing we'll also throw in before we shift, well, we'll probably finish this chapter 5 section. We can also mention something about metallic character. Metallic character is a horrible thing to mention. I think it's just dumb, but it's in the book, so we got to talk about it. And where's the most metallic element? The what side? The left side. There we go. Okay, our metals are on the left side of the periodic table. Our nonmetals are on the right side. So the further we get to the left, the further away from the nonmetals we become. So we must be becoming more metallic. Okay. Nonmetals also tend to be grouped on that staircase in the upper right-hand corner, which means the further down we get, the more metallic we'll become. Okay. We will use this definition of metallicity at least until we come up with a better definition towards the tail end of chapter 4. Okay. Which I'm just going to sort of briefly touch into before we leave. What we're looking at now is the second half of chapter 4. If you have not read that chapter yet, please do so before Tuesday. Because if you want to talk about mind explosions, light and electron orbitals is usually one that destroys brains. Okay? So at least have a baseline by having read the chapter.